Welcome everybody. So by this session, we begin our course on mathematics. As you have seen in the introduction, we will be considering the concepts of derivative, limits, and continuity of functions. So derivative, limits, and continuity of functions, which are actually very much familiar to you, but as you might have observed, we are not moving in a proper order here. Usually, limits are defined first, and using limits, continuity and derivatives are defined then. But as you are very much familiar with these concepts and their definitions, and following your textbook, we start with the derivatives, move to limits, and using limits, we will try to explain and discuss continuity. Okay, so let's consider derivatives first. So before formally defining derivatives, we'll examine a physical condition where derivatives are made use of. So we actually start with an example. Consider the situation of a bus traveling on a straight highway. Suppose the distance traveled by the bus in time t or in time x. So I choose two variables here. Say y to be the distance covered and x to be the time. Usually the variable t may be chosen for time, but for convenience I choose x here. And suppose that y and x observe a relation as y equal to f of x, or this just means that the bus travels f of x units of distance within x seconds or x units of time. Again, I repeat, this expression y equal to f of x, where y is the distance and x is the time, means the bus travels y or f of x units of distance in x units of time. Right. If it is the case, let's try to find the velocity of the bus. For now, choose this point to be x naught, the point of time. See, this is the time x naught, and the bus moves on in this direction, and when the bus reached at this point, time was, say, x naught plus delta x. See, this is a technique in mathematics where we use delta to designate small changes. Right. So time changed a little bit here. Or to be a little more general, let's come to this later. Say this is the point x naught, and say this is the point x1. 2 points in time. Right. And from this expression, we know the distance traveled at this point is actually f of x naught, and the distance traveled by this time x1 is f of x1. Right. Now can we make use of this information to find the average velocity between these 2 points of time? As we know, velocity is actually or the speed or whatever, in that sense, is actually distance by time. Right. So what is the actual distance covered here? F of x1 minus f of x naught. Right. It was at f of x naught actually, and moved to f of x1 when the time was x1. Divided by how much time elapsed to conduct this motion. The final time is x1 and the initial time is x0, so the time elapsed is x1 minus x0. Right. So this actually gives the average velocity between x0 and x1. The average velocity between the times x0 and x1. Now we make an adjustment that we try to bring x1 closer to x0. Try to bring x1 closer to x0 in the sense that we are trying to find the average velocity within a very short span of time. Within a very short span of time, to designate that, we will just use x naught plus delta x, and delta x means a very minute small change in the time. Right. So if it is the case, using the same technique as this, can we find the average velocity attained by the bus in this time interval? Let's make use of the same formula. The final distance here will be f of x naught plus delta x. Since the distance at time x is actually given as f of x, so the distance at time x naught plus delta x will be f of x naught plus delta x. So the velocity, the average velocity will be f of x naught plus delta x. The final distance minus initial distance will give us the distance travelled, minus f of x naught divided by x naught plus delta x minus x naught. So that x naught and minus x naught will be cancelled out and we will be left with delta x. Right. So this actually gives us the formula to find average velocity within a very short span of time around x naught or just after x naught. Right. I hope you will note this down. I have to clear this for the sake of space. The next concept is to make use of this formula for average velocity, like f of x naught plus delta x minus f of x naught divided by delta x. Can we make use of this formula for average velocity to find the instantaneous velocity at x naught? So what is the difference between instantaneous velocity and average velocity? Average velocity is actually the velocity observed in between two time points or in a time interval. The average velocity attained by the moving object or the bus within a time interval. But the instantaneous velocity is the velocity measured at a single point of time. Usually in our vehicles, in our car or bus or whatever, we used to find this instantaneous velocity in our speedometer. Right. So, can we make use of this formula to find the instantaneous velocity? Obviously we can. And the technique here is to bring these 2 points arbitrarily closer. X naught and x naught plus delta x has to be arbitrarily closer, which means x naught plus delta x will be very much close to x naught. What does that mean? X naught is assumed to be very small, like something near to 0, very close to 0. So when we make delta x very much smaller, considerably very much smaller, x naught and x naught plus delta x will be arbitrarily closer together, and we can use this formula then to evaluate the instantaneous velocity at x naught. So the velocity at x naught can be found using the formula, the same formula, f of x naught plus delta x minus f of x naught divided by delta x, but delta x assumed to be very small. Remember, very small in the sense very much small, which is which does mean delta x is something very much closer to 0. We will re-encounter these terms in concept of limits for sure. So this will be a little more comfortable then. So remember these two formulas. We found the average velocity in a time interval, and from that we know how to find the instantaneous velocity at a point of time. Now let's see an example of this. As you have seen, suppose our bus travels and the motion is actually described using the function y equal to 2x square, where x is the time and y is the distance covered in x units of time. Now find the average velocity between 3 seconds and 4 seconds. Suppose the time is given in seconds and distance is given in meters. So find the velocity between 3 seconds and 4 seconds and find the instantaneous velocity at 3 seconds. So we are trying to find the average velocity between 3 seconds and 4 seconds and the instantaneous velocity at 3 seconds. So what was our formula? Like our x0 is 3 here and x1 is 4 here, right? So the formula was actually f of x1 minus f of x0 divided by x1 minus x0 to find the average velocity. And what is f of x1 here? F of x1 means f of 4, y equal to f of x has this expression 2x square. So substituting x equal to 4 in this expression, we will get y equal to 2 times 4 square. 4 square is 16, so 2 times 16 is 32. So f of x1 is 32 minus f of x0. So x0 is 3 here. So substituting 3 in this expression, we will get 2 into 3 squared. So 2 into 9, which is 18, divided by x1 minus x0 is 4 minus 3, which is 1. So this is 14. Don't forget to mention the units. So the average velocity between time 3 seconds and 4 seconds is 14 meter per second. Right. Now what's the instantaneous velocity at 3 seconds? Right. So we'll use that expression including delta x. So f of x0 plus x0 is 3 here. 3 plus delta x minus f of 3 divided by delta x. So what is f of x here? 2x square. So what is f of 3 plus delta x? 2 into 3 plus delta x whole squared minus what is f of 3? 2 into 3 square, which is 18 by delta x. We don't know what is delta x here. So that implies 2 into, this is of the form a plus b whole squared. So a squared plus 2 into a into b plus b squared. See, when I write delta x square, delta is actually a single term. Never confuse it as delta into x square. So delta x whole square minus 18 divided by delta x. So I'll clear this. So that's equal to 2 into 9 plus 6 delta x plus delta x whole square minus 18 by delta x, which is equal to, so we can multiply 2 inside the bracket, 18 minus 12 delta x plus 2 delta x squared minus 18, so by delta x. We can strike off these 18 and 18 since they are of opposite signs and the same term. We'll get 2 delta x square minus 12 delta x divided by delta x, and we can cancel out delta x from both numerator and denominator, since we can take a delta x outside as a common element here. So which will be 2 delta x minus 12. Right. Now remember, why did we put a negative here? It's positive, right? So remember, to find the instantaneous velocity, we were actually supposed to make delta x very much smaller, something very much near to 0, right? So as delta x becomes smaller and smaller, 2 into delta x also will be moving towards 0 or become smaller and smaller. In that sense, as delta x is made arbitrarily smaller, this will be approximately equal to 12. Right, this term will be negligibly small and the whole quantity will be approximated by 12, and giving the limit, units, will get 12 meter per second. This actually gives the instantaneous velocity of the moving object or the bus in this case at 3 seconds. So the average velocity between 3 and 4 was 14 meter per second, and the instantaneous velocity at 3 seconds is 12 meter per second. So I hope the concept is clear. Actually, we can make use of derivatives here, and we haven't defined derivative yet. So for now, we are supposed to move on using this formula. You can find a few more examples in your textbook. I hope you will work them out. Right. So the next concept is slope of a tangent. We are actually hitting the bush. Like we are trying to explain the same concept in 3 different ways. Right. The second one is slope of a tangent. Slope of tangent. So I hope you are very much familiar with the concept of tangent. Tangents are actually the lines drawn with graphs. Suppose we have a graph of a function here. Suppose we have a point here. The tangent to this graph at this point is the line touching the graph exactly once, and that is at this point. The line meeting the graph at exactly one single point is called a tangent. Right. So suppose this is the tangent at this point. Say this graph is of the function f. So the vertical angle is, or the y-axis is marked with f, and the horizontal angle is marked with x. This function, this graph is of the function f of x. Right. So choose this point to be x naught. So our task is to find the slope of the tangent line. I call this line to be t, the tangent line, at the point x naught. The slope of the tangent line at x naught. We make use of a technique as we have seen in our case of velocity. Instead of considering a single point x naught, we consider 2 points. Say I have another point x1 here. And now I draw a line connecting these 2 points, and which does not intersect the graph anywhere else. Right. So the new line, I call it S, is a line intersecting the graph exactly twice. Such a line is called a secant line. A secant line. You know how to draw graphs and how to mark points on the Cartesian coordinate system. So if this is x naught on the x-axis, this point will be, the corresponding point to this will be f of x naught, and this point can be identified as x naught, f of x naught. And if this is x1, since we have x1 on the x-axis, we will be having f of x1 on the y-axis, and this point will be x1 f of x1. Right. Now we make use of the formula to find the slope of a line. Consider the secant line S. We have 2 points of the line, and we can use those 2 points to find the slope. So if x1, y1, x2, y2 are 2 points on a line, the slope of that line can be evaluated as y2 minus y1 by x2 minus x1. Okay, if x1, y1 and x2, y2 are 2 points on a straight line, the slope of the straight line can be evaluated as y2 minus y1 by x2 minus x1. So what are the 2 points available here? We have x naught f of x naught and x1 f of x1. Right. So the slope can be evaluated as f of x1 minus f of x naught divided by x1 minus x naught. So this gives the slope of the secant line, not the tangent line. Now the next question arises, can we make use of this formula to find the slope of the secant line, to find the slope of the tangent line? Obviously we can. What if we bring x1 and x0 closer? We bring x1 closer to x0. So this point will be traveling along the curve towards this point. And if you make them infinitely closer or very much closer, the secant line will almost coincide the tangent line. The secant line will almost coincide the tangent line. So we can think of the tangent line as the secant line which is passing through the single point x0, or we can evaluate the slope of the tangent line as the slope of the secant line passing through x0 and a very much closer point of x0, f of x0. Right. So as we have done before, we will make smaller arrangements here. Instead of x1, this is the tangent, instead of x1 we choose x0 plus delta x. To denote, it is somewhat closer and closer, and the corresponding function value will be then f of x0 plus delta x. And if it is the case, how does the formula change? How does the formula change? The new available points are x0, f of x0, x0 plus delta x, f of x0 plus delta x. Right. Then the new formula to find the slope of the tangent, the secant line will be f of x0 plus delta x minus f of x0 divided by x0 plus delta x minus x0, which will be delta x. Right. This is nothing but the same formula we have seen in the other case of velocity. Right. So, to make x0 and delta x arbitrarily closer, we have to assume that delta x is very much small. So this expression actually gives us the slope of the secant line, and to find the slope of the tangent line at x0, f of x0, f of x0, assume that delta x is very much smaller, very small. Right. Like we found the instantaneous velocity. Right. In fact, the concept of velocity in the motion and the slope of the tangent in this and the concept of derivative for a function are exactly the same. We will be moving towards derivative in our next session. So, this is how we find the tangent of a tangent to a graph at a particular point. Right. So, what was the strategy? We considered a secant line which was passing through two different points and found the slope using 2-point formula. And we made the 2 points closer and closer. To express that, we use the delta x here. So that's how we find the slope of the tangent to a curve or the graph of a function. Right. But in a practical sense, we may not be drawing the graph, the secant line, or even the tangent line, but we'll just use the formula. Let's try with an example. Find the slope of the tangent to the graph of the function f of x equal to x squared plus 1 at x0 equal to minus 1. Right. So the question is to find the slope of the tangent of graph of the function f of x equal to x squared plus 1 at x0 equal to minus 1. So we are not going to draw the graph, the secant line or the tangent line, but we will just use the formula. So remember the formula is f of x0 plus delta x minus f of x0 divided by delta x, where delta x is assumed to be very small. Right. This was the proposed formula to find the slope of the tangent to the graph of the function f at x0. Right. So let's evaluate this. So f of x is x squared plus 1. So what will be f of x0 plus delta x? Obviously x0 plus delta x whole square plus 1 minus f of x0. See, x0 is minus 1 here, so we can directly substitute that from here itself. Let's don't make unnecessary steps. So f of x0 is f of minus 1. F of x is x square plus 1. So f of minus 1 will be minus 1 square plus 1. Minus 1 square is 1. So 1 plus 1 will be 2. divided by delta x. Right. See, this is of the form a plus b whole square. So let's expand it formally. Minus 1 square, so 1 plus 2 into minus 1 into delta x, which is minus 2 delta x plus delta x square. Remember, this is not delta into x square, this is delta x as a whole term squared, plus 1 minus 2 divided by delta x. See, we have a 1 here, another 1 here, both comprise to form a 2, and we have a negative 2 here, so all these 3 will be cancelled out eventually. So what is left out here? Minus 2 delta x plus delta x squared divided by delta x. So we can take out a delta x common from the numerator, and we can cancel that delta x with the denominator, which will give us minus 2 plus delta x. Now assume delta x is negligibly small. Delta x is negligibly very much small, and if it is the case, we can assume this to be approximated as minus 2. Right. So the slope of the tangent of graph of the function f of x equal to x squared plus 1 at x naught equal to minus 1 is negative 2. Right. So this is how we practically make use of this formula to find the slope of the tangent to the graph of a function. Right. So now we move towards the core, the derivative. We directly and formally define the derivative as the same formula we were using so far. So derivative. So let f be a function. In fact, we cannot say f to be any general function. F has to be a differentiable function, in fact, in some cases. So consider, for now, consider f to be a function and define f of x naught plus delta x minus f of x naught divided by delta x. The same formula we have been using so far to find the velocity, the slope of the tangent, and this quantity approximated for small delta x or very small delta x gives the derivative of the function at x naught. Right. So the derivative of the function at x naught, f dash of x naught, can be evaluated as f of x naught plus delta x minus f of x naught divided by delta x for very small delta x. So what we were doing so far, we were evaluating velocity as a derivative. We have found the slope of the tangent as a derivative. Right. So remember the formula, f dash of x naught is given as f of x naught plus delta x minus f of x naught by delta x. Remember again, for very small delta x has to be approximated to 0, approaching 0. Perfect. So now let's, as a part of, for the sake of completeness, let's see an example. Differentiate or find the derivative of the function f of x equal to, say, some mx plus 2 at x not equal to 10, where b or m is a constant. We don't know what is that. So suppose m is any constant, find the value of the derivative of this function f of x equal to mx plus 2 at x naught equal to 10. Right. So let's find what was the formula to find the derivative. F dash of x naught equal to f of x naught plus delta x minus f of x naught divided by delta x for very small delta x. Remember, I will repeat it several times as it is that important. So f of x equal to mx plus 2, so what is f of x naught plus delta x? X naught is 10 here, so we can directly replace this from here itself. F of 10 plus delta x and f of 10. So what is f of 10 plus delta x? M into 10 plus delta x plus 2 minus what is f of 10? 10m plus 2, right, f of 10 divided by delta x. So expanding this, we'll get 10m plus m delta x plus 2 minus 10m minus 2 by delta x. So this 10m, this negative 10m plus 2 minus 2 will be cancelled out. So what will be left? M delta x divided by delta x is left here. So we can cancel out delta x and delta x. So what is left here? M. Since we don't have any delta x left in the final answer, there is no point in just claiming delta x to be very small. It's okay, it's obvious. It does not depend on delta x anymore. So the derivative of the function y equal to or f of x equal to mx plus 2 is m. Remember that we have given an information x not equal to 10. See, this derivative actually does not depend on the value x not equal to 10. You can make an attempt by replacing 10 with 5 or 7 or whatever. This actually does not depend on this value. So for any given value or at any given point, the derivative of this function, this linear function, will have the same derivative m. Right. So that's all about derivatives. We have to learn certain properties of derivatives sooner once we discuss limits and continuity, maybe in the very next session.